Good evening to all. My name is Krishnan, and it is my pleasure to welcome all of you for our fifth and final webinar as a part of #Q Thursday. Before we start, I request everybody to join us for 1 minute of silent prayer. Thank you. This week's topic is how to use quantum to solve real-world problems. You will get a brief overview of quantum computing, and then you will learn why we use quantum computing to solve real-world problems, as well as how to use quantum in the near term. Finally, you will get an overview of quantum applications and a quantum development walkthrough. I would like to introduce our speaker, Mr. Simsarul Vengaserri. Mr. Vengaserri is a quantum tech enthusiast who is working to solve real-world challenges. He graduated from NIT Calicut and is currently leading quantum innovation at UST Innovation Labs, where he solves top problems in healthcare, retail, financial services, and more. He is very interested in applying technological innovations to solve real-world problems, and he loves helping others to learn the same. A warm welcome to you, sir. Before we start, I request the audience to kindly keep themselves muted. If you have any questions, you may post them in the chat. All doubts will be clarified in the Q&A session towards the end. Now, I invite Mr. Vengaserri to take over. Sir, please.
Yeah, thank you, Vishwesh. That was a very kind introduction. And really need to thank everyone for joining the session. And this is a very great initiative, part of the IIIT Kottayam. And I really want to thank Dr. Lincy, to connect with me and allowing me to take part of a session like this with all of you. It's my pleasure to, really join and participate in the session. So I want to really thank all the organizers to setting up this session. So let's get started. So I think this is a fifth of this Q Thursday series, and I think I heard some of you might have already been to the previous session. So you might have already got a background. So can I get a quick round of hands? How many of you have at least participated in the previous series of this Q Thursday initiative? Yeah, we can see. Yeah, some of you. Okay. Great. At least, yeah, we have some participation. Yeah, but yeah, sure. So I will be covering the the basics in a brief way. So mostly focusing on what are the near-term applications we have. So my goal with this webinar series is to this particular presentation is to get you familiar to some of the approaches we can take with accessing quantum computing to solve some real-world problems. So what are the different ways we can actually adopt? And so I'll just give you a walkthrough during the session. So I hope you will get, by the end of this session, you'll be able to know some of the approaches that we are actually using to solve some problems. So let's get started. So I'll share the screen. Give me a second. So yeah, please let me know if my screen is visible to you.
Yes, Simsar, it's visible. Yeah.
Okay, great. So just want to know one thing before we start. You know, just want to know how many of you think quantum computing is actually currently used in practice to solve some real world problems today. Like, I just want to know if anyone thinks that quantum computing is actually used today to solve some problems. So can you give a hands up if you think so? It's already used, whether it is currently used. I think yeah, I think Shivani told like it's currently. Do you want to comment on this? Like it's, I just want it to be a conversation. So what do you think it is currently used? Like, if you're really interested to comment, like, I found a message. There's quantum key distribution. That's right. That's a very interesting place. It's currently being used. Bitcoin. Okay. Okay, we'll see. What else do we have? Okay, so let me ask you this: like, how many of you think quantum computing will be used in practice in the next 5 to 10 years? I mean, better than any existing classical solutions. That's what I mean. Yeah, I think some of you think that. So some of you are very pessimistic and how quantum computing are. So okay, so let's see. So the goal of this session is to introduce you to some approaches that we can follow in the near term. So maybe I'll get started with. Okay, so what I'll be covering is like I'll just give you an idea of the different quantum computing like basics of what I mean by quantum computing. And like what is near-term applications and what are the different approaches we can follow. So I really like to hear from you before I start with the presentation. Like, if some of you have already looked into what quantum computing is, I would like to hear your perspective. So if some of you can speak up, that will be great. So anyone want to volunteer? What do you mean by quantum computing?
This is Venkat. Hello.
Yeah, ready.
Hello.
Yeah, Venkat, please go ahead.
Hi, this is Venkat. So quantum computing is basically using quantum phenomena on computing so that we can process the data much more faster, as it contains two main principles like entanglement and superposition, which can enhance your processing speed to a greater level in exponential way. That's what quantum computing is, basically.
Yeah. Great. Thank you, Venkat. I think that's a very good definition. That's great.
Sir, shall I come in?
Yeah, Brinda, you can also.
Yeah, this is Brinda. So I think as quantum computing in many places, either computing very complicated problems or whatever it is, we run out of memory space. So while using this quantum computing, I think there is a greater advantage. So instead of zeros and ones, you have different states where we store all this information. So your memory, it can be unimaginable if you're able to really master it. So I think that's important.
Yeah, that's great. I mean, that's the one. Like, thank you, Brinda. I think that's a very good point you brought up. So there are some good definitions. Anyone else want to take a chance to define it? So so I heard some of the applications you have mentioned, like quantum key distribution, like in cryptography. So that's one area that you already know. Do you know anything else that we can use quantum in the near term? I mean, do you have anything to share? Like, just want to know your perspective currently. Protein folding? Yeah, great. So that's a good, interesting use case, because most of this quantum mechanical systems, if we try to simulate them in a classical machine, right, it's not optimal. So quantum computers are great at doing that. Okay, so so let me give you let me start the session like so the core idea is that like right now we have classical computers, and you know how the classical computers are designed, right? So we like if you look back to the history, right, we have this Turing machine model initially discovered, and the challenge and the goal was to uh, realize a computer that can actually work the Turing machine model, right? So, but we initially started with the binary bits, like because we invented transistors. Transistors can be operating as a switch, so it's like you can have on or off. So we used transistors to build our initial earlier versions of a computer, so that it can have a memory and it can process. So what I mean by processing is that it stores some information and then it's processed, and then we have some other information stored, processed information. That's what computers usually do, right? So and if you look back at the history, right? So the transistors has been evolving, and we were scaling this computing power for a very long time. But what happens is like right now we are trying to scale down the size of the transistors. And now what happens is like we reached a very small level where quantum mechanical properties are inevitable. So those kind of phenomena, something we have to take into account. So the transistors may not work the way we would expect when we take it to a very small level, because we can see the electrons can tunnel and through various small barriers, which will make it other than the on and off. So it will not be working as a classical computer. So so why we fight and building smaller transistors, like it's time to leverage those quantum effects. So it's like when I look at the long term, right, eventually if we want to increase the computing power, we need to really scale, think about leveraging the quantum effects that is there, and then try to use that in our computing. So that's why I think quantum computing is inevitably something that we'll have to work on, because we cannot scale classical computers without considering the quantum effects we might have to encounter at that small level. So I'll just give a quick introduction to what a qubit, because some of you might have already familiar with this concept. Just like in classical computers, we have bits, which is like 0 or 1. Qubit is the basic foundational unit for any quantum computing. So it's like when we define qubits, right, it's not just 0 or 1. It can be both. So like if I talk about the physically, what happens is like if you look at a small electron, I mean in its ground state, and if you suppose you provide some energy to that system, that electron will excite, right? That's how it actually works. So but in reality, if you try to electron can be in the ground state and excited state at the same time. So it's counterintuitive to what classical bits are defined. So that kind of a system can be modeled as a foundational unit, which is called qubit, which is like not just 0 or 1, but it can be both at the same time. So that's what we have as the basic unit for quantum computing, qubits. And so why? So one question is just like I mentioned, right? Now we had this classical computers built initially, but now we have to take in the quantum effects into consideration. And now what is the advantages we are going to get? Like if you model our computation in a quantum state and then do processing there. So like we already have a lot of algorithms that is like proven to have speed up compared to classical algorithms. One such algorithm was Grover's algorithm. I'm not going to the details of any of these algorithms, just to give you an idea why we need to think about quantum algorithms. So this Grover's algorithm is like one early algorithm that we discovered, where like to search for an element in an array. For example, if you want to search for an element in a database, classically, if there are n items there, you have to look for each items at least once, right? If it's sorted, so in an unsorted database, so it's like the worst. So the order, the complexity will be order of n in the best case, right? But we found that there is an algorithm which is a quantum algorithm which can be done with only square root of n queries, which is faster than the any possible classical algorithm. And similarly, you might be also heard about Shor's algorithm, because I heard some of you mentioning about Bitcoin and stuff, because some of the cryptographic systems we use are based on some of the asymmetric key cryptographic, like based on RSA and all those things. Those things are based on assumption that the classical algorithms cannot factor large numbers, and there is already a quantum algorithm which can do factoring in polynomial time. So which means very efficiently. So all this crypto systems can be broken with that. So I just want to mention another algorithm, interesting, because most of us think that because quantum actually works in a only gives probabilistic, we can only design probabilistic algorithms. No, we can actually design deterministic algorithms. What I mean by that is, like, deterministic algorithms are those algorithms, when you give an input, it will always give a certain output. It don't give a probabilistic result. So it's also possible to design quantum algorithms that are deterministic. Just want to give you a thought on that. And there are already a lot of problems that are theoretically proven to have speed up compared to the classical equivalent, and especially in quantum machine learning. I mean, some of the machine learning algorithms have already proven to have speed up. Like, for example, if you look at k-medians, it's like it has a quadratic speed up already. Well defined. And the only challenge here is that some of these algorithms actually require the data to be in the quantum state. Like, it has to be quantum data. Like for example, some of the exponential speedups are obtained when the data is actually represented in a quantum state, and then apply this quantum algorithm into that. So like, we are not taking into the consideration how this the state can be created. So that's one area, that one challenge in really applying it. So yeah, so why a quantum computer does better than a classical algorithm is, like, just like you mentioned, we have so many quantum mechanical phenomena that we can leverage, like superposition and entanglement, and all of these things can be used in our algorithms to create better output. So that's one thing. And secondly, the Moore's law, which was stating that the transistor size will grow in every 2 years. So that is also failing, right? Because now we have to encounter the quantum mechanical phenomena at the bottom level. And now there is a law that is coming up, which is like we'll see quantum computers grow every year, like double the number of qubits. So which is already happening in the last few years. And one thing interesting about quantum is that, like, if you look at the number of atoms in the universe, like visible universe, it's something around 2 power 300, right? So, like, suppose we want to create a classical computer with all the atoms in the universe, with the visible universe, you can only create a a computer of that size, right? So if you if you want to create an equivalent quantum computer, you will just need a 300 qubits, which is like 300 electrons. So that is the kind of scale that we will get in terms of what we can do with quantum computers. And if you look at the best supercomputer we have today, like, it is of the size of a football field right now. It's so big, and in equivalent quantum computer with only 50 qubits will be able to do equally good equal computation power. So which is like 50 qubits, right? So that's a scale. Like, one requires a huge power to like, for example, the best supercomputer requires a huge nuclear power plant kind of a power to actually run that kind of like supercomputer. But the quantum computer will be very energy efficient. So these are something we can really see why we need to use quantum computers in the near term or the future. And so we see that like there is a lot of progress happening in quantum computing, especially in the last few years. And like almost the number of qubits we can see doubling almost every year if you look at. And the interesting thing is like in adding a single logical qubit to the existing quantum processor, it's equivalent to doubling the number of doubling the computational power in the classical case, right? So it's actually when we think of doubling the qubits, it's actually way superior. We are getting huge performance improvements compared to the classical. Yeah, so I'll just talk about some interesting applications that comes like what quantum computers are really good at solving. So just before that, I just want to pause to let you, if you have any questions regarding what a qubit is, or basically why we need to use quantum computing. Let's have it, because I just mentioned it very briefly, assuming that some of you have already gone through the prior sessions. So if you have any questions, maybe we can discuss it right now before moving on. So any of you have any thoughts? Anything you want to clarify right now before we move on? So can any of you volunteer? Something that you have learned, like why do you think we need a quantum computer? Like, just want to know if you have are you getting what you are following with what I'm saying? If one of you can
Could be optimized for computations. We can do at a faster pace than the normal computers.
Okay, so okay, great. So that's I'll continue if you don't have any questions. So there are 4 interesting use cases. Just wanted to initially mention in high level. I will go to the details later on, but there are 4 interesting problems that quantum computers are very good at solving right now. The first one is optimization problems. For example, if you look at an optimization problem, what is it actually why is it very challenging for classical computer? Because if you have a very large number of parameters in your optimization problem, the running time actually grows exponentially. Just think about any optimization problem and see what are the different constraints that you have. So as the number of parameters grow, the running time grows in a classical computer. But quantum computers are very good at solving problems, especially optimization problems, when it has a large number of parameters to optimize. So that is there is a huge set of use cases that related to optimization that we can really use quantum computing to solve. And secondly, machine learning. I just show you already mentioned that there are so many machine learning algorithms that have proven to have advantage over the classical algorithms with significant speed up. So that will make a lot of machine learning algorithms to be implemented on a quantum computer. So that's an area there where we have a lot of applications. And thirdly, chemistry, because most of the chemical reactions and molecular reactions, these are quantum mechanical reactions, right? So if you're trying to model that kind of a quantum mechanical system on a classical computer, you will not be able to model. The best way to do it is actually simulate it on a quantum hardware, right? So it have all the features. Like if you want to model a superposition, it's better to use a quantum hardware that can actually has a superposition. So most of the molecules are currently being modeled into a using a quantum computer. So that's a very, very active area of research. And also in cryptography, especially because we have in classical computer, we already have seen, right? There are a lot of algorithms like RSA which is like an asymmetric crypto system, and that is already proven to be solvable. I mean, the factorization problem is already proven to have a faster algorithm using quantum computers. So that is why we have to think about solutions, how we can actually secure this communication channel, and quantum actually actually gives a lot of there is a theorem in quantum mechanics called no cloning theorem, which says that if you have a quantum state, you can't exactly clone that state. So if you try to clone it, you will change this that state of that particular qubit, and it will not be the same. So you can't exactly copy. So normally, if you look at a classical network, right? If you want to send an information from A to B, what happens is why do we even do encryption? Because we don't want anyone in the middle to read it, right? So we try to encrypt it, and then the receiver can decrypt it so that the information is secure. But think of it, if you have a no cloning theorem, you can't clone the the state. Then that's a very interesting area to look into. And the quantum key distribution is a way you can actually distribute keys between two persons securely. So I will give you a walkthrough of all of this during this presentation. So later on we'll see some of the approaches how we can take in the near term to actually solve some of these problems. Yeah, so these applications actually spread across a lot of domains. So if you look at any domain, right, you have some applications where the quantum computers can really come and solve. Yeah, so now I want to take you to what I mean by the near term. So if you're good with so far, or if you have any questions until now, let's have it right now. So are you good so far? Okay. Yeah, I was not getting the chat messages when I was presenting. Okay.
I think we're doing really good, Simsar. We have some lively discussion going over in the chat, and it's really interesting. I think we're going in a really good direction.
Okay. So I'm not seeing the chat. That's okay. So I will try to look at it often. Okay, great. So
we'll keep an eye out for questions in the chat, and we'll let you know maybe in a question answer session then. So that'll leave you that part of it.
Yeah. So what I would really like, if you have any questions, we can actually cover in that early stage itself.
Participants, please feel free to unmute yourselves and ask questions. That would be really great.
So if you have any questions, right, either you can post it in the chat so that one of you can read it, so that we can clear it at that stage itself. Otherwise, we'll just continue. We'll have some questions at the end, but before going to some of the details, maybe it's better to clear the questions at the early stage. So okay, then I will discuss about what I mean by the near-term intermediate scale quantum. So this is the it is the current stage of quantum computers is currently regarded as a near-term intermediate scale quantum. So what I mean by the NISQ devices is that these quantum processes are actually having some noise which need to be corrected, and so that's why we will have to when we think about solving and designing a solution, we'll have to really think about how we can mitigate this noise. So that's a thing we will need to consider in our algorithms. How do we approach when we approach this kind of devices? And the intermediate scale, what it means is right now we have very limited set of qubits, and the gate fidelity is very moderate, right? So what I mean by gate fidelity is that what is a quantum algorithm? It's essentially we have some quantum states, and then we apply some quantum gate operations, and then we get some quantum results, just like any classical algorithm, right? If you look at the foundation into the gates and all, you have some binary states, and then you apply some logical gates, and then you get some result, and that is the algorithm, right? Similarly, what I'm in quantum it's almost like you have a set of qubits in a starting stage, and then you apply quantum gates, which is actually the evolution, how the quantum state is going to change when you apply that gate, and then you get the result. So right now we have this intermediate scale devices which are having a limited number of qubits, and the gate fidelity is very moderate. What I mean by fidelity is like the gate. So if you want to apply a particular gate operation, if the gate is not well, because the noise can interfere with this system, right? So you may get a result slightly different. So you have to account for that, error that can happen. So yeah, so the NISQ devices, the NISQ algorithms are designed to work with this kind of devices, which are noisy. Yeah, so let me go to the next stage. So yeah, just wanted to give you a brief idea on what are the different devices we have today. One is so we have an approach using to realize this kind of a qubit using superconducting qubits methods. So many companies like Google, IBM, and Rigetti and other startups are like considering this approach to actually realize a qubit, which is very interesting. So it's like normally if you have a circuit, right, like superconducting circuit, and if you place an insulator in the middle, the current can't flow, right? So what really how the superconducting qubit is realized is that if you narrow the size of the insulator, the qubit, the electrons can actually tunnel through that, right, because of the quantum phenomena. So what happens, you can actually control and create a quantum state from that. So if you want to really look at how this is built, it's very interesting. And like one very interesting thing about this superconducting qubits that these are having fast gate times, and the disadvantage is that this has to be, the states are very vulnerable. This kind of quantum state that is created can be easily collapsed by any variation in the external temperatures. So one thing I just wanted to clarify is that, like, we usually talk about qubits and the number of qubits as the computational power of a quantum computer. But the thing is that it's not just about increasing the number of qubits. We have to have qubits that are with less error rate. So if we have a 1,000 qubit quantum computer, it doesn't mean anything. But if you have a 100 qubit quantum computer that can work as a logical qubit, then that is a very powerful. So we actually coined a term called quantum volume, which to measure how a quantum computer's performance. So so when we think about near-term devices, we have to look at how do we error correct this quantum when we do any algorithms on it. So quantum correction can be an external different algorithm. So once we apply the quantum error correction, we'll be able to realize some logical qubits. So, but the disadvantage is that we'll have to use multiple physical qubits to actually realize a logical qubit. So when we hear of a quantum computer, we have to really think how much logical qubit it can actually represent. So another model was like topological qubits. This is actually worked by Microsoft in the early stages. So it's currently thought to have a very good it is expected that this kind of topological qubits can significantly reduce the error, but its realization is a very challenging thing. So I think Microsoft is currently working on implementing this kind of a qubit. And this is another approach using trapped ions. There is a startup called IonQ. They are very they have realized some very stable, highly efficient qubits, and they have also managed to.
Excuse me, Simsar. I think your slides aren't changing. We're still seeing the slide which is near-term intermediate scale quantum.
Oh,
yep, now it is.
Okay, sorry for that. I thank you for that. Okay, so let me know if it's changing now.
It's on the slide which is near-term intermediate scale quantum.
Okay, it's not changing. Okay, let me then do it this way.
Okay, yeah. Now it's on the slide which is NISQ devices. Yeah.
Okay. I'm sorry. Thank you for that clarifying that. So So I was just talking about some of the different approaches this qubits are realized these days. So superconducting qubit is like one of the common qubit approach that we have followed, like by most of the companies. And I was also mentioning about the concept of quantum volume, which is like which like the number of qubits, physical qubits is not the measure, but how much logical qubits it can actually represent is what measured by So I'll just so topological qubit was the one I mentioned that Microsoft is actually currently working on. So this kind of qubits are expected to have highly it can greatly reduce error. That's what is expected. And trapped ions is like this is what is currently done by IonQ, and this is currently being regarded as a very stable kind of an approach, and it have already achieved high gate fidelities, and they have also managed to scale it to very good level. So this is a very interesting approach to realize a qubit. So there is also a way to there is a concept that is pioneered by D-Wave, which is quantum annealing. So this is like a special purpose quantum computer. It's it's actually used to solve a certain kind of optimization problems. So it's designed specifically to solve that kind of problems, and it will actually find you the in optimal state very fastly. And they were able to scale that kind of a devices very quickly. Now I think they have around 5,000 or something qubit a quantum annealer. So that is another approach, and it's done by D-Wave. Yes. So so that's some of the approaches we have with realizing qubits. So right now we have quantum simulators that are available so that we can test the noise. Like for example, this is a simulator we currently have, which is built by IISc Bangalore. It's called Qiskit Agash. It's worked on top of the Qiskit framework. So we can actually model various noise parameters on the simulator and see how our algorithms will differ when we have a certain kind of noise in our algorithm. So the simulators, some of the simulators are already there for all of us to use, so that we can see how our algorithms will perform under noisy scenarios. Yeah, so I want to go to this is the most interesting part of this session. So we just want to this is what I wanted to cover with you, how to use it in the near term. So if you're good with what I mean by near term, we can continue. So if you have any questions, we can discuss now.
I think we had a few questions in the chat, and we have Korean Benoy also raising his hands to ask a question. So if you want to unmute yourself and ask a question, Korean, that would be great. Okay, I guess that was a mistake. There's also a couple of questions which turned up in the chat, so maybe I'll read it out.
Yeah, sure.
Okay. Okay. Right. Yeah. Just give me a second. The chat's moved on quite a bit, and there's a lot of lively discussion happening in there. Okay. So Rajith wanted to ask, can any program written in a traditional computer, such as a Turing machine, be written on a quantum computer?
Yeah, that's a good question. So, just want to clarify one thing, because if you want to think this way, right? Classical computers are a very special case of a quantum computer. It's a limited case of a quantum computer. So if you want to define that way, because the qubit is like a 0, 1, or a superposition of both, right? So you can actually say classical computers are a subset of quantum computing, which means any classical algorithm can be implemented on a quantum computer, theoretically. But if you look at the practice, right, because in the near term, because of what we have with quantum computers, the kind of noise and all those things that we are facing, so we would actually only implement some of the algorithms that can actually give speed up when using a quantum computer on a quantum computer, and the rest of the things will be implemented on a classical computer. But theoretically, any classical algorithm can also be implemented on a quantum computer.
Thank you, Simsar. Shivani asked, I'm still confused as to whether it's a physical qubit when you're saying logical or topological qubit, or is it actually a mathematical representation you're talking about?
Okay, yeah, that's a good question. So what I mean by physical qubits is like, think of one qubit, right? Like a superconducting qubit. So if it's like you have a way to represent a qubit, but the thing is that an external noise can interfere with the state of the qubit. So if you have a state that is like equal superposition of 0 and 1, and then an external noise can influence that and it changes to something else. So it's not actually representing. So we need to have an error correcting mechanism. So to do that error correction, like if you look at the classical computers, right? We had this issue in the classical computers also. So in the olden days, like if there is a information to be transferred between A to B, so if you just send a single bit of information, because of some noise, that bit value can change. So what we did is we duplicated. So we send multiple same message multiple times, so that we take the majority of the what we receive. So that's an error correction mechanism where we are expecting some error to happen there, and so we had to use multiple classical bits to actually send the information of a single bit. So similarly, in quantum computing, we can't do actually cloning because of the no cloning theorem. So we have other techniques to actually realize quantum error correction. So we may have to use multiple physical qubits to actually realize a single logical qubit. Logical qubit is what I mean by valuable qubit. So physical qubits is actually the realization which will have some error noise to it. So we may have to use multiple physical qubits to actually realize a single logical qubit. So those kind of logical qubits actually gives the quality of the quantum computer. So if you say you have a 100 qubit logical qubit, quantum computer, that's very good. But if 1000 qubit quantum computer that is not having proper error correction, that's not very useful. So that's what I mean. So is it clear to you, or do you want any further questions? Yeah.
Yep. Shivani says, yep, thanks.
Okay.
I think we have gone over most of the questions. We'll keep an eye out for any more too. Encouraging all the participants to turn on your mic and ask questions if you would. Thank you, Simsar.
Okay, then I will. So I will go to the interesting section, part of the presentation. So how do you actually, work with this kind of near-term devices? So this is our thing. So we have algorithms that are there are some algorithms that are near-term feasible because of the noise, and how do you actually reach to a stage that is possible to implement in the near term? So let's discuss this. So I just wanted to introduce to some of these concepts, and it's a very interesting ideas, and there is a lot of opportunity to really research and build solutions. So we just wanted to introduce some of the most popular approaches that we are following, to solve some problems in the near term. So I'll just talk about what I mean by quantum-inspired algorithms and give you an example of what I mean by that. And there is a concept of hybrid variational algorithms that is also very commonly used in the near term. And there is a way to actually create value using quantum computers, not necessarily by increasing the speed up. So I will discuss that too. And in the quantum cryptography, like I mentioned, there are interesting things that we are currently actively doing in the practice in the real world. So we'll go through that, in quantum annealing also. So these are the 5 topics that I just wanted to introduce you to, so that you can further research and learn about this. So these are the most commonly followed ways to solve in the near term. So I'm just starting with quantum-inspired algorithms. So it's a most of us think that because quantum algorithms are, we have a lot of algorithms that are, already researched and proven to have speed up, but some of our qubit realization and the hardware is in a very early stage. But the interesting thing is that those kind of quantum algorithms have already started to give value without even the presence of a quantum computer. So let's look at how that is actually done. So what I mean by quantum inspired algorithms is normally when you have a quantum algorithm which have speed up, can you actually create a classical algorithm? Inspired by some of the ways we have actually implemented the quantum algorithm. So it is already, there are some researchers who have worked on it, and they have found that we can actually create classical algorithms inspired from quantum algorithms. And some of them have already seem to show some exponential speed up. So it has actually, helped the research community to build some better classical algorithms. So I'll show you some of those, how it's actually done, so that you can look further into those. And it's already demonstrated in practice to work very well. So actually, there is Scott Aronson is a very famous quantum scientist. So he's actually joked about this kind of algorithms as like quantum computing applications that are realizable with 0 qubits. So you don't need any qubits, right? It's actually some classical algorithms that are inspired by some of these quantum algorithms. So the key idea of this is like it's called dequantization. So if you have a quantum algorithm, can you actually create some classical analog to that quantum states and forming a model for dequantization? And sometimes it gives a potential speed up. So there has been some interesting research happening in this way, and we were able to find some better classical algorithms. So if you look at some of the quantum machine learning algorithms, right? For example, so I just want to give an idea of how this kind of algorithms are actually created. So for example, some of these algorithms that actually have exponential speed up, like principal components. So these actually requires a quantum data to be prepared. So most of our current existing solutions have classical states of data. So if you have a way to actually find an analog to these quantum states, we can actually some of these algorithms can actually work in the classical computers itself and give a speed up. So if you really look at the quantum and classical computing, right? P is usually used to define the set of algorithms that are actually can be very fastly solved using classical computers. And the BQP is actually the class of algorithms that can be solved very efficiently using a quantum computer. But the interesting thing is that we don't yet know what is the is every quantum algorithm can also be efficiently solved in a classical computer. We just don't know if P and BQP have any relationships. So which makes it interesting that because any quantum algorithm that have speed up can potentially have an equivalent classical algorithm with similar speed up. So we don't know, there is no proof that it can't be the case. So that's why, when we have a very good quantum algorithm that is already working, so some researchers actually go and see, is there a classical algorithm that can be created in a similar way, which can work very well on a classical computer. So there has been there is a research paper that's recently published, running this kind of quantum inspired algorithms on classical algorithms and seeing how it works, and this research paper have actually demonstrated it. Some of them was working very well, and so the core idea is that we need to take a very fast fast quantum algorithm and see what can be quantized in that kind of a algorithm and use a dequantization framework. So it can be there are a couple of dequantization framework we can follow, and if you're able to successfully dequantize that algorithm and create a equivalent classical algorithm that have a significant speed up, and you can actually run it on a classical computer. And this paper actually I've just referred in in this particular research paper have actually worked showing a particular algorithm that has previously we didn't know any classical algorithm that can run very fastly for that kind of a problem, but knowing that there is a quantum algorithm that can run fast, they actually dequantized it, and they were able to create a classical algorithm that can actually run with an exponential speed up. which means we found a better classical algorithm because we had a better quantum algorithm. So that is a very interesting thing I just wanted to share. Even though we didn't have any quantum computers, we can the quantum research can actually be used in real world, and it has been actually used in practice also. So there was an application actually done by Fujitsu and UK Space to actually optimize the space, tackling the space waste, right? So optimize the time to take and the time and the fuel required to actually run the spacecraft to actually remove the satellite waste to a disposal orbit. So they actually modeled this kind of an algorithm in a way using a quantum inspired optimization algorithm, and they were able to demonstrate it in practice. So these are some interesting ways like this is actually used in practice today. Yeah, so you have any thoughts or questions on the quantum inspired algorithms? Otherwise, I'll move to the variational algorithm.
I think we are good on the chat, right?
Okay. So what do you okay? So I think no questions in the chat, right? Okay. So I will. That's one interesting area of research that's actually going on. So I will then now discuss about the variational algorithms. So this is a way we can actually use in the near term to solve interesting problems. So if you look at the quantum computers we have today, right? As I mentioned, the issue of noise is the key thing. So if you have a quantum state and if you want to apply a quantum gate on that, and if you want to apply a series of quantum gates, right? If you increase the number of gates, so the problem is that the noise also will increase. So it is right now with NISQ devices, you can actually run short depth circuits, which means you have few gate operations on a qubit, and you get the result. You measure the result and you take it. So in a way, if your algorithm only requires short depth circuits, we can actually run it well on a near-term quantum computer. So, but how can we actually make a really interesting problem into something that only requires short depth circuits to be used? So that's where we like the variational hybrid algorithms actually come into practice. So here, just like I mentioned hybrid, we use the classical computers to actually increase the performance of the quantum algorithms. So one such interesting variational algorithm is QaOA, quantum approximate optimization algorithm. So it is used to solve the combinatorial optimization problems, especially on the near-term devices. So if you look at just like any quantum circuit, it's actually a series of quantum gate operations. So it's like you have a quantum state, and it's like you apply some quantum gates, which is like an energy function on that qubits, right? And if you want to execute a very large depth circuit, it's going to be challenging on a near-term device. So you have to leverage how you can use short depth circuits to actually solve the problem. So to do that, we have like concepts like there is a decomposition formula, Trotter-Suzuki, and you can read about it more. So what it actually does is like it actually help you to create short depth circuits for a circuit that otherwise requires a large number of gate operations. You can actually create a series of short depth circuits, and it's actually combined with a classical optimizer, and it will feed some optimal parameters to the quantum circuit, and based on that, the quantum circuit will iterate. I mean, this quantum and classical algorithms will iterate for a certain time, and then we'll take the result out, and based on a stopping criteria, which can be the number of iterations that this particular thing have to follow. So it's like this. So we have this classical algorithm giving some optimal parameters for the quantum circuit, and it will run that quantum circuit, short depth circuit, and then it will again the result will be feed into the classical algorithm, which will find another set of optimal parameters, and then it will again run on a shortest short circuit, and eventually we'll be able to get a result after a few iterations. So this is a very interesting approach. I mean, it's very commonly used these days, like to build some use cases. So it's also used in practice. Like I think 2019 or something. So it's Barclays, it's a bank. They also demonstrated for a practical use case. So I'm just referring to that link of that research. So like there was a problem for transaction settlement, trade settlement, which is like if you have a large number of trades to be settled, these trades can be dependent on various other parameters like other trades. So what is the optimal trade settlement strategy you can follow so that the total value of the transactions is huge? I mean, while meeting all the constraints, right? This is a problem of high value, right? I mean, a lot of trade is actually happening. So if you can actually settle the trades in optimal way, it will actually create a lot of value. So this has actually been demonstrated to work with this has been worked like to run on an IBM device using QAOA, and like it's used. But if you look at it, we used only a limited number of qubits. So it's not used in practice, but it's possible. They created a proof of concept that this kind of an algorithm can be solved using QAOA. Yeah, so that's briefly about how the variational hybrid algorithms work. So if you have any questions, we can discuss about it.
I think we can move on.
Okay. Yeah. So this is like another interesting approach. So like if you look at the near term, right, we will be seeing a lot of classical and quantum algorithms, and both of these processes working together to solve a problem. That is the near term approach we can think about. Another interesting way we can solve problems in the near term is through quantum value. So we usually talk about a speed up, right? Quantum algorithms to come up with better speed up than classical algorithms, so that we can use quantum algorithms. But there is an interesting way we can actually use quantum computing, not necessarily looking for any speed up. That is like this is actually like presented by a startup called Protein Cure, who are trying to model drugs and on a quantum computer. So what they figure out was like so if you like, for example, if you want to predict then toxic molecules from a large set of molecules. So if you have a very large set of molecules and you want to predict which of them are toxic, and so say you have a classical predictor which can flag 90 out of 100 to be toxic. So you actually have 10 false negatives in that case, right? So what if you can actually run it on a quantum predictor as well? And if the quantum predictor give you 10 of the molecules to be toxic, and because both of these have some errors, and both errors are uncorrelated, and if you run it separately, right, and if you look at it in combined way, 5 of this probably maybe quantum may be able to predict some of these toxic molecules that classical actually missed to predict. So because both of these have some uncorrelated errors, we can actually use both of them, not necessarily for any speed up, but to get a value to predict something that classical actually missed to predict because of the uncorrelated errors. So that's a very interesting way Protein Cure actually worked on. And yeah, so they were able to reduce the error by using this approach. But the disadvantage is it's not guaranteed to the quantum algorithm to have any orthogonal error to the classical method. But it's a way quantum algorithms can actually give value compared to classical algorithms. Yeah, so that is another near-term approach we have. Also, in the quantum cryptography, like I mentioned, this is a very actively and most researched area. And in terms of practicality also, like there are a lot of companies actually working on this area, because it's very clear that once we have a very powerful quantum computer, a lot of our existing public key cryptographic schemes are going to be broken. So the only challenge is that we are not able to run this kind of an algorithm like Shor's algorithm on a real quantum computer, because we don't have the logical qubits required to run this Shor's algorithm right now. But what can happen is, like there is a way to actually there is an attack that is like harvest now, decrypt later. So what I mean by that is, like you can actually harvest some of this encrypted data. So many of this data that is encrypted have a very large shelf time, right? Because most of this data is valuable, for a very long time. So for example, if this data is valued for 10 years, and say, for example, we can have a quantum computer that can run Shor's algorithm and be able to decrypt this kind of, RSA encryptions in 7 years. So what we can do is we can harvest this data right now, and in 7 years we'll be able to decrypt it, but the data is valued for the next 10 years, right? So there is a risk before, even though the threat is not now, but because the shelf time is there, it's going to be a risk. So most of the companies are actually thinking of ways on how we can actually use some methods so that the quantum algorithm, even it's harvested now, it's not decrypted in an immediate time where that data is valid. So there is like a lot of interesting work. So they're also working on this area, so we can actually mitigate this kind of risk actually caused by quantum computing, but quantum itself provides a lot of ways to solve it, right? We have like what we call as quantum random number generators. This is like this we have a lot of devices these days in production, like to create quantum random number generators. So many of the random number generators classically we use as pseudo-random algorithms, which is actually not an best randomness, which can be actually, the randomness can be actually predicted in some way, if like in certain cases. But quantum random number generators are going to be perfectly random if it's well implemented. So that's an area like we already have a lot of hardwares that are coming out, and even last year, even one of the Samsung phone is like announced to have a QRNG chip inside that device. So it's like it's going to be there for a lot of devices are going to have this kind of quantum chips embedded in them. And we also have a concept of quantum key distribution to actually securely transfer the keys between two nodes, so that we can use those keys to actually encrypt data. So this kind of approaches actually give us overhead over the challenges caused by quantum computers itself. And there is also a way we solve this using some post-quantum cryptographic techniques. So like we know the factoring of a large numbers can actually be solved very well with quantum computers, but there are some other ways we can actually implement the cryptographic techniques so that quantum computers are also not able to break it. Like there is concepts like lattice-based cryptography, and there are a few other areas that currently validated by the NIST to actually come up with a standard protocol that we can actually use instead of RSA. So it's currently, I think, in the progress of standardizing that. So once we have that kind of a framework, we'll be able to use it immediately. So this is kind of a threat that actually quantum computers pose before even we be able to decrypt that kind of immediate data. So it's actually so this is so we are actually working. We have actually in our lab has worked on this kind of problems, and worked with creating models that can address security challenges, and how we can use like QRNGs and QKDs to actually create a framework to securely transfer the data. So these were some good near-term approaches that we have. So I just want to pause for the questions. So what do you think about this? Like, just want to hear from you. So this, what is your thoughts on this near-term approaches? Okay. Yeah. So so if you look at a lot of use cases, right, they're actually worked out using some of these techniques because we have to work with short depth circuits in the near term. We can't run a very large circuit and get a speed up. So that's a long term idea we have. So any questions so far? I feel like all of you are like either you are like clear or you are not getting. I mean, you're missing what I'm saying. So okay. So anything that you want me to clarify a little bit more?
Could you maybe go into the dequantifying part of things a bit more? That would be really good.
Okay. Okay. Yeah. So the quantum inspired algorithms, right? Okay.
Yes.
Yeah. So so it's a very interesting area. Like the dequantization. What I mean by that is like you can actually refer to this paper to know more. This particular thing, it has more details, but briefly what we can say is like, so if you look at any like quantum algorithm that has significant speed up, like there is a, for example, there is a concept called sample and query access. It's a dequantization framework. What I mean by that is like there is a result saying that you can actually so you can actually the quantum state preparation is something that like using it has quantum states involved, right? But you can actually sample and query and do an equivalent operation using classical computer with very efficiently. There is an algorithm to do that. So that makes that sample and query access a dequantization framework. So what we actually have to learn in that case is like some of these ways the dequantization actually works. So I don't know if you can look into this paper, maybe you'll be able to learn more. I can't explain it very simply right now, but it's very interesting because some of these dequantization algorithms are very efficient. Because of that, that's why we will get the speed up. So it's actually a very actively researched area, and so something like you have to look into more detail. So you can refer to this paper to learn more about it.
Thank you. I believe we have a raised hand. You can unmute yourself and ask questions.
Hi, this is
Kumar.
Hi, this is Anuj here. Okay, so just want to I think clarify one point where it was being discussed around the PQC part. I think the point which need to be clarified under the mapping and just for a very high level understanding. So this the PQC approach is actually the target is to actually go for securing the asymmetric wherever the transactions are involving the asymmetric keys. They are actually vulnerable to these quantum challenges, security breaches. Okay, the where we have the symmetric keys, it is still I would not say there is no issue, but they are still considered to be secure. Okay, so that is a point I think I just wanted to clarify, and so people can understand because how this PQC, because PQC itself, there is a decision pending and directions need to come from NIST, National Institute of Standards and Technology. So they need to give the guidelines related to the algorithms and the protocols which will be used for this particular PQC approach. As I think it was being explained that there are a lot of actually algorithms and protocols like lattice and elliptic curve, and there are a hash code. Some many other algorithms are there. So, but which one is actually preferred approach? That guideline is still awaited from NIST.
Yeah, thank you, Anuj. I think that's a good point. Like you mentioned, like right, the asymmetric, the most of the security issues are caused in the asymmetric key encryption. The symmetric key is like mostly secure, but what happens in reality is like the symmetric key encryption actually requires the keys to be there at the both ends. So we practically use asymmetric key encryption to actually distribute the keys. So that way, you know, that if we can like secure that asymmetric key encryption using some post-quantum algorithm, I think that would be great. You know, because symmetric key encryption is not an easy one for any quantum computer to solve. Even though there are some result, it can actually solve it faster, but symmetric key encryptions are very secure. Yeah, thanks, Anuj. And any other questions? So if you have, like, if there is time, I wanted to discuss about quantum annealing also a little bit more in detail, how we can actually model a problem solving at least at a high level using a quantum annealer. So if you're good, I will move on. So I just want to tell you that you know, building your own QRNG devices is possible. So you just need a few components and you can actually do it anyhow and test out and like have fun with that. So so I'll just talk about quantum annealing in a bit more detail. So right now, you know, like, you know, why do you think quantum computers are very good at solving optimization problems? Like, any thoughts why quantum optimization problems are a very good candidate for quantum computers? You have any thoughts? Anyone want to volunteer? Okay, okay, then I will just you know, briefly talk about it. So like if you just think of a you know, what does an optimization problem need to solve? It need to find out maybe you need to maximize or minimize an objective function, which means to find a global minima of a objective function. That is the core idea of any optimization problem. And if you want to reach to that optimal state, I mean the minima or maxima, normally classically you will have to try out all the possibilities and then see which is the best, I mean which is the global minima or some like minima, local minima, and so on. But then like quantum computers, because it can model a landscape of an optimization problem like very efficiently, it can actually reach the global minima through quantum tunneling and other quantum mechanical properties, which makes this quantum computing like optimization problem to be a very efficient problem to solve using quantum computing, because it can use some interesting properties of quantum mechanics to actually come to that global minima. So for example, if you're just thinking about a, you know, like, you know, everything in the world, right, in the electrons and all those, everything want to stay in their ground state. That is like, so if you try to excite any like give some energy to a quantum system, it will, if you keep it like undisturbed, it will actually go back to its ground state. So that's a natural phenomena that happens. So the idea is that, can you model a problem such a way that the ground state is your solution, and you can represent that to like, So that you can you model a problem such a way that the ground state is its solution, and all you need to do is like if you model it like that, you just need to keep the the electrons to go to the ground state, and that will be a solution. That's a very high level way I can explain why how this optimization problems are solved using quantum annealers. So like the interesting thing is, like for example, we were considering a problem for solving traffic flow optimization. So this is like a problem. So I just wanted to tell you how to model a problem to solve optimization problem to solve optimization problem. So for example, I'm just considering a problem of a traffic flow. So what I mean by a traffic flow optimization problem is that, like, consider a city and you have a lot of cars in the city, and there are a couple of roads each car can take to reach its destination, right? So there are a wide variety of possibilities each car can take to reach its destination. So the objective function is that can you find a path for each of these cars such a way that the total congestion of the city is minimized. It's a very complex problem because each car can take a lot of different paths, and how do you classically come up with a solution? The best way is to, find out all the different path possibilities and come to a solution, right? So it's actually a very complex problem for classical computer to solve, especially if the number of cars and number of roads are very large. So this can be modeled. So we need to mathematically model this problem. So for example, quantum annealers like D-Waves device are very optimized to solve certain kind of problems like quadratic unconstrained binary optimization, which is like a optimization problem where you specify in a particular way. So I'm not going to the details of that, but what we can do is, like, you can actually model this problem using some qubits. So in a very simple way, right? Like for example, if you can model we actually try to recreate this problem in our lab and try to solve it. So like what we need to do is, like, we have to model, for example, like if there is a path, so you have to use qubits to represent each cars, and then like if there is a path that two cars can take, we actually increase the coupling. There is a coupling parameter we can choose, so that so it basically we are trying to make that least preferred state. Like we don't want to make too many cars to go through a certain kind of path, so we can actually model it that way. And like if you model the entire traffic flow state into a quantum computer, and then we leave it so that it can find its ground state, and that ground state will be the best path for each of the car to take, so that the total congestion is minimized. So like I just wanted to introduce you to this kind of approach. So there's a research paper already out there. It's already been implemented. So I encourage you to look into how this is actually converted into a quadratic unconstrained binary optimization problem, and it's actually solve it. So like and like we'll be able to get some result which states that this cars can take this paths, and all in all, with all this paths, the total congestion is minimized. So I just want to hear some thoughts from you. Any questions you have so far on the problem or how it can be solved? Are you good so far? I'm not. Okay. So
yeah, I think we're good.
Okay, great. So so these are the some ways we can actually solve in the near term. So I'm just skipping a couple of slides which I was explaining in more detail. So like I just briefly So what I can say is like we initially we had a quantum computers work for a specific kind of problem using D-Wave and so on. But now we are in a very interesting stage where we have more interesting use cases unlocked with near-term quantum devices. Now, what we need to achieve in the later stages, like we need to have more logical qubits so that we can actually run a lot of quantum algorithms actually to work to have something called quantum supremacy. Like even though Google demonstrated a quantum supremacy for a particular problem, if we have a more number of logical qubits, we'll be able to get very superior results. So that's the next stage of quantum computing that we can expect. I hope you have got something valuable through this session. So send any feedback if you have any thoughts or suggestions. Yeah, so that's it.
Thank you very much, sir.
Yeah, thank you so much. I mean, it was great to meet you all. I mean, I think we have still participation of like something that we started. A lot of people stayed back. Really thankful to all of you. So thank you, everyone, and thank you, Dr. Lincy, also.
Thank you, Simsarul, for readily accepting, and it was really good. Like we had, this was the last session, like as we planned in the series, and you kind of summarized everything from basic to applications and real world problems. It was good to have you. Thank you. Thank you so much. Yeah.
Thank you so much.
Thank you. So for the participants, actually, we'd like to have a recap of things, like what was happening throughout the webinar series. So, Simsar, if you could stop sharing, maybe I'll just show some of the. Yeah. Thank you. And, so just a recap of what we were doing this past month. So we had a webinar series of around 5 sessions. So it started out with this small poster, and at that time I think I had only contacted 3 people, and I thought we'll have 3 sessions and stop or something. I didn't know what could be the continuation or anything. We just started with this, and now we are here. We had around 5 sessions. We had a good combination of people from. We had Professor Prashanta K. Panigre here representing the academia. So and many researchers who are closely working with quantum computing. And quantum from quantum core researchers to quantum applications in the industry, and these are some of the highlights of our program. Actually, we had first session around 257 registrants, and around 62% were students, and we had a good percentage of industry people and faculty from academia, and also some other positions also. We had a good combination, around 20% were from industry, and from Q Thursday 2, 3, 4 and 5 we had around 150 plus participants, and just wanted to show you how we could reach new people, because we got around more than 40% new registrations every time we put up Q Thursday posters and Q Thursday when we try to promote for the continuing sessions. And so finally, at I think when we had Simsar's session, for the last session, this was the percentage, around 48% have not attended any of the previous sessions, and I think even then they could you all could have a good combination of understanding of what is happening in the real world, what is the current research or what is the current things that are happening in the quantum field. And overall, unique participants, we actually had around 500 plus, around 527 registrants we had. And I hope we could reach to many people who are really interested and want to know about quantum. So that was the aim of Q Thursday, to get people to know, get introduced to the field from the wonderful experts. And I'd like to thank all these people because our director and registrar and also our PIC academics, they were very motivating, and they were the background in creating this. And all the faculty members, staff and students who were really instrumental in promoting this event, and they keep on sharing and sending the invites to everyone, asking everyone, reminding everyone to join, everything, like all those people from IIIT Kottayam, and especially the speakers who made this event very wonderful, because we had very resourceful people who were ready to join during their busy schedule and busy work, in that they were able to join and help. And Q India had a part of co-hosting 2 sessions in the series of Dr. Sonali and Dr. Rajiv. They were part of Q India, and special thanks to Mr. Rishi, because he was helping around in from starting this Q Thursday. I was in contact with him, and he was helping and advising me on many things and guiding me. And the special mentions on the event managers, our students, Mr. Vishwesh, Ms. Arundhati and Ms. Aditi, they were only managing the whole event, and they introduced the speakers. They did their part very well. And thank you for the IT support from IIIT Kottayam. Special mentions are Mr. Siju sir, who constantly every week he will ask me about okay, how many participants you got, whether the session went well, everything he inquires and he makes sure. And Bijo was throughout the session helping and in the background setting up everything, and Jitin also was very helpful when Bijo was not there. So they were instrumental in uninterrupted internet service, because that everything was happening online. And some of the special mentions, without these people I would not have thought of this event. So Dr. Nadarajan and Dr. Arunadhan, who were the mentors of me from PSG College of Technology, my guide Dr. Jesse Johnsey from NIT Calicut, and special mentions because they were motivating and they were giving me feedback, Dr. Kala, Dr. Edwin and Dr. Christina from IIIT Kottayam. And my students, Mr. Vishnu and Mr. Aditya Vardhan, because in the background from designing posters, by getting participants, for everything they were in the background. And Vishnu used to remind me of things, many things which I forget, to send link to the MC people, and so many little tiny details also they were helping a lot. And thank you all. Thank you so much for joining and making this event a success. Thank you. And feel free to drop your feedback and suggestions to this email ID, lincy@iitkottayam.ac.in. Thank you. Thank you all. Thank you so much.
Yeah, thank you everyone.
Thank you, Simsar.
Thank you so much.
Thank you, Neha. Thank you all. Your participants made this event very lively, and thank you for being here till 6:30, 7. Sometimes it goes till 7 o'clock. Yeah, thank you. Thank you all.